In this video, I'm talking about arbitrary mesh finite volume method using an Arakawa C-Grid. Previously, we talked about the Cartesian grid numerical modeling, which is done on squares where the velocities are stored at the edges, and scalars like pressure and density are stored in the cell center. In 3D, it looks like this. And in the diagram, I've showed, x direction. I put u here just to show it that's the x face, w here to show that's the z face, and then v here and in the back to show that's the y face. But in fact, you actually store here u, v, and w are here. Like just like we see the flow is moving this way, it can move from the top of two squares like this. Moves here, it also moves up and down, it also moves, I guess there's another direction I guess it can move. But anyways, irregular grids, or I guess arbitrary meshes look like this, where usually it's just hexagons and pentagons. Here's a pentagon. And similar, we have a face, but there's 5 faces instead of 4, or 6 faces here, and then there's 5 here. And there's the cell center is kind of the same situation. There's only one cell center per cell. And then in the z direction, you can think of it like this, where underneath one of these shapes, the same shape is below it at every single level. And under this is a bunch of pentagons. So this is kind of what it looks like. Center is here, the faces are like here. And of course, this is actually going to be not as long as it's shown here, or it could be, depending on how you define this. So, because it's Arakawa C-Grid, scalars, like we said, are stored at the cell center, and fluxes like velocity u are stored at the cell face. Okay. And we talk about cell center as Ci, so the first cell center would be C1. Maybe you have 100 of them, there would be C100. Edge would be the edge of a single cell. So if you have a cell with 6 sides, there would be E1 through E6. And you would have many more edges in total, but per one there's usually 5 or 6. And then for the gradient, because we calculate it like this, where we have the scalar, the gradient of a scalar, which is usually we never have the gradient of a flux. It never really happens in general. But the gradient of a scalar, you have the 2 scalars at the 2 cell centers, and you go across perpendicular to the edge that's between those 2, and the distance between them, for example, we can call the delta x EI. That is going to make the gradient stored at the cell edge. And divergence, which is a sum of all of the contributions at each edge, for example, 6 contributions, that's going to be stored at the cell center. And then the curl, which is how much something rotates around something, if you're talking about velocity for the flux, is stored at QV, which is the corners. There's 5 corners or 6 corners. So now we're going to derive the finite volume method divergence operator, and the derivation doesn't come from this paper, but the result is written in this paper, Conservative Transport Schemes for Spherical Geodesic Grids by Skamarok in 2011. Now we're going to talk about the equation d phi, where, or actually I don't know if it's called, I'm going to call this phi. I think phi is this, so I'm not sure what to call this, but let's just call it phi. d phi dt is equal to some right-hand side, which is a function of phi, which is scalar, and the flux is v, is equal to the negative divergence, which is convergence, of that scalar times v. And an example of this is this equation. Notice that this is partial, this is total derivative, but same kind of thing. This talks about how the mixing ratio, for example, mixing ratio of water vapor, how much water vapor there is compared to air, how that changes over time is how much um, the water vapor converges into a region, or fluxes into a region. So this could be, I guess, flux convergence, because the velocity, takes the Q, the water mixing ratio, into a region, and so it would increase in that case. So for the derivation of this, we start here. We take the volumetric average, which is 1 over the volume, integral over the volume of both sides, and we know that volume is a function of Ci, which is the cell center. So that's why we write this, right? Now, for this integral, what happens is we have d dt comes out. I mean, the 1 over v is still there. And an integral of phi dv, this part is equal to phi bar, where that's the cell average. But we don't really need to do anything to it. Once we get it, we can just straight up take the cell average and put it back in the equation when we solve it for the next time step, in this case. And we apply, I believe, what we're doing here is we're applying the divergence theorem. So this divergence goes away, and this actually becomes a circle integral along the edges instead of the cell center, so Ej. This stays volume of Ci, and this part comes here, and then we're left, we need to have these, according to the divergence theorem, we need these normal vectors that are normal to an edge. And we also need the length across the edge. So this is the length across the edge. And the normal vectors are going to point perpendicular, maybe some are going in. I'll talk about that later. So when we convert this integral from which is continuous, into a discrete sum, because we are doing this on a computer, we do not have access to continuous solutions in real life. So we sum over all j, over all, because they call it the number of cells. So actually this is the number of edges. So basically sum over all Ej, basically. We can say it goes from, maybe, for example, we could write it as j to the number of Ej. Or, yeah. J into the number of edges. And then this will become a flux, which represents this part. Flux operator is what we'll call that, the Fej. And just correct that. So, I will show right after what this means, how do you calculate this, but you can, think of it, you're running through every single edge. All you need is the length across that edge from center to center, which is constant, I believe. The volume of the cell depends on the shape of the cell. But for a single cell, basically we do this calculation for each cell. We go to this cell, and we need information about the shape of that cell. But then, other than that, these distances are pretty much the same. We just run a sum around the edge, and we just need to know whether the normal vector is positive or negative, and then we go to the next cell, do it again, go to the next cell, do it again, go to the next cell, do it again, and we do that for all our cells, and that's how you solve the equation. And so what is this flux operator? Here's the second order version. So I plus 1/2 is stored at the edge. So that's good. That's where we need our flux to be. So if we didn't have this scalar, it would simply just be the velocity on that edge. But in this case, we also need the scalar phi here needs to be on the edge as well. but it's not. It's on the cells, so we need to take an average. 1/2 times the two added together gives you what the value is approximately with a linear interpolation between to guess what the flux contribution from a scalar would be. And then also third and fourth order, we have this one equation. If you want it to be third order, you make b 0, so this whole part goes away, and then this is third order. Fourth order would be including this, and then we have this weird like sine thing as well. How this is derived, I have no clue, but I'm sure there's some paper somewhere that talks about it. But yeah, again, this is from the Skamarok 2011 paper. So, but now we have solved the right-hand side of the equation. This here is, this is equal to the right-hand side, which is equal to this. But we need to solve for this, not for we do not need to solve for the time derivative of this. We need to solve for this. So now what we do is we use Runge-Kutta 3 to do the time discretization, where R of t is that sum we just came up with. So we calculate the sum, add it, multiply it by delta t over 3, and add it to the solution currently. That gives us the a intermediate step version. We plug that back in, solve the equation again. This time it's delta t over 2, gives us another intermediate step. And then finally we plug it back in one more time, only times delta t, and add it to that current time. So it's kind of getting these fractional steps that add up to eventually be the next time step when you add it to the current time. So t is the current time, t plus delta t is the next time. So maybe delta t could be like 15 seconds, for example, or 1 second. It's limited. You cannot go down to infinitesimally small on a computer, so that's why we have to do this. So here's an example of the right-hand side. Here's a number of EJ. Let me see, why did I call that T? That should be F. Okay. Yeah, so in this derivation, I called it L, so we should probably keep that the same. Let me keep this, make sure this is exactly the same. So I think this is just an example. Okay, this is NEJ, LEJ. And okay, so for example, we're going to solve our equation, do a time integration, do a spatial integration at the 0th, I equals 0 cell. So if we go back up, that's this cell, okay? So I'm just going to grab this picture, copy, and just bring it down here so we can, we can see. I'll just put it here so we can see it. Okay, so we need the volume of this. I'm not sure the equation for the volume of or in this case, volume would be an area, but if we're talking about, right now, let's just talk about 2D. If we're in 3D, we need the actual volume. In this case, volume is just an area, so I'm not sure, there's probably some way of splitting this into some triangles or something and getting in an area of this. Yeah, there's definitely a way of doing this by just calculating all the triangles area and adding it together. So we need the area. We need the area. That's what volume is. So volume of C naught is equal to area of C naught in this case. And then we sum over all edges, multiplying by our value. So, the value of U at our edge. Let's just say that. Let's just call this F actually. So we have our flux. We've done the calculation as we just talked about. This calculation here, we've gotten this at every single edge. So that's what this is. So we run through all of our, edges. Let's just say that M is equal to N of EI. We run through all of them. So the first one is, the flux at that edge plus the flux at the next edge plus the flux at the next edge. In this case, we go 1, 2, 3, 4, 5, 6. We go through all edges. And we also need, for each of these cases, we also need this LEI. So we need the length across, which I believe in this case is probably constant. Though maybe not, I'm not sure. It's probably the same always. So these you can probably just take out. Volume of the cell is one volume, and then here is, oh yeah, I see. So I made a typo. So in this case, it was the velocity at the edge. Yeah, so the velocity at the edge. Here's our flux function. Well, actually, this whole thing is the flux function, see? And then, each of these actually should have a normal vector. So this should have NE1. This should have NE2. This should have NEM. Okay, so that's kind of just showing what this looks like, for a single cell. We run through all of its edges, multiplying by the flux, the normal vector, the length, cross the edge, dividing by the volume. That's the finite volume method. So here's an example. These are going to be our normal vectors. And here's the tricky part. For normal vectors, if we're talking about Cartesian, you need to be consistent. We need to be consistent about where these are. So every single, if we have a grid next to it, and we say, now when we're talking about this grid, we say the right one is pointing this way, and then suddenly for this grid, we say the left one is pointing this way. Now, maybe for this grid, the right grid, we say the flux is pointing this way. But then when we're talking about this one, we say the left one is going this way. Sorry, let me restart. So we're talking about this one. We say that the flux, the normal vector goes this way. Sorry, not the flux. Normal vector goes this way. But then we wanted to find the normal vector goes this way. Then when we describe our new one that's right next to it, suddenly the left one goes this way, which completely counteracts with this flux. This would be not conservative, where the value of the fluid moving in is not conserved. So, so in the case of Cartesian, it's very easy. We simply say the normal vectors are always pointing to the right in the x direction and always pointing this way in the y direction. You can actually switch it, and this is what it would look like. So the divergence, this is 1, 2, 3, 2. These are the values of the flux at the edge, okay? And we know if an arrow is pointing out, away from the cell center, we say it's positive. If it's pointing towards the cell center, we say it's negative. So this would be -1 plus 2 plus 3 minus 2, which is equal to +2. That would be the value of the divergence. Here, we have +1, right? This is out, +1 plus 2. minus 3c, and minus 2. So basically you can see the sign of the 1 changed, and also the sign of the 3 changed. It still equals 2, so therefore the divergence is the same. As long as we stay, as long as we keep these consistent. Now the issue when it comes to something that, a grid that looks like this, maybe this is a triangle, like how do we come up with a method for initializing these ends so they are consistent for every single grid? I think that's very complicated. There's probably very complicated algorithms that do this, because it's not as simple as how we define it for here. It really doesn't matter what direction we choose as long as we're consistent. So hopefully I can figure that out in another time, how that's done. But for now, I'll just understand the theory of it. So now we're going to talk about finite volume method for arbitrary C-grids. Where I got this information is from the paper Unified Approach to Energy Conservation ... by Ringler, Klemp, Skamrock, Thuburn. I'll give a very brief overview of this. So we have our cell. We call this primal cell mesh. They called it PI. I'm going to continue to call it CI. And then you have this thing called a dual mesh, which is a triangle. At every single, there would be multiple triangles basically at every single one. And these are a secondary mesh, kind of for visualization, but so we can kind of think about this better. In reality, the way a computer stores it maybe is less complex like this is. And yeah, we can see here's some examples of those normal vectors I'm talking about. And they also have these vector, we call them N6, but we have a vector here, another type of normal vector that's always pointed to the left of the normal vectors. And these will be useful for calculating the curl later, Yeah, and this is what I was saying earlier. You must use an algorithm to define n normals, n, which are normals, as at each edge, so they're always consistent. And then the t normals are always to the left of the n along an edge. So first, how to do the gradient operator. Well, actually, first let's talk about the divergence operator. So the divergence operator, we can write it like this, and yeah, I know it's out of order, but same thing. This time you might see, the sum has this weird thing, EJ in EC of CI. We know what EJ are and ECI are, but what is this EC? This is just kind of a notation that they made up, and so they have in table 2 in the paper, they talk about it. So I'll just tell you which this one means. This means all edges in, the edges that are in a cell, basically. This EC means that edges that define the boundary of CI. So this EC is all edges of CI, and we have EJ inside of that set of edges. And then we again define NEJ is 1 towards CI at EJ, and negative one away from CI at EJ. And here's an example of how to solve one of them. So here we're just going to talk about this case right here. So we want the divergence, which is sum along the edges. So first we get the volume of our whole thing, which is area. We divide by it. And each time we have a flux function times a distance. So we have the flux, flux number 1 times the length, which is going to be this length, which is, now we see where the dual mesh comes in. It's the length of an edge of one of the dual meshes. So it's a way of storing that dual mesh. Anyway, storing that value, I guess. So we have the length of the first one. And then we have the normal, which is pointing away, so it's positive. Next one, it is the length of one of these dual meshes times the n, and it's negative because it's pointing to the center. And dot, 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 go through all of them. This one's out, this one's in, this one's negative. And so it will look like this. L1, F1 minus L2, F2 plus L3, F3, where again, F is flux at the edge. Minus, minus, plus. This is the divergence, and the divergence is stored here because you do this calculation and kind of see how much this value fluxes into the center. For gradient, we use, instead of EC, we use CE. What does CE mean? That means two primal mesh cells that share an edge E. So here's an example. If we look at E, which cells share this edge? The answer is this one and this one. There are no other cells that share this edge. There's two. So this is saying that for each cell, we'll see, actually, yeah, this is going to be for J. Okay, this here, okay, I made a mistake. This is going to be J. Okay, this is I representing which cell it is in the cells that share the edge EJ. So we calculate the gradient for every single edge. Before we calculate it, we go through cell, calculate the divergence, go through cell, calculate the divergence. Now we go each edge individually. Then we go each edge. So there's a lot more calculations that need to be done for the gradient. And then we have our scalar, which is going to be here and here. And then we have negative nj. So here, for example, this is positive, right? We can say, this is, let me think. Okay, so let's just talk about, we first start with this I, okay? So this is H1, this is H2. This is phi1. It's the value here. C1, C2. If we talk about C2, phi2 is here. N is pointing towards it, so N is -1, but it's negative of it, so our contribution will be positive. So it's positive, the value at C2, which we will call phi2. Here, N is negative, N is positive, but it's negative of positive is negative, so it's negative contribution times phi1. So that's why we have right, so this is, they could take a negative out. So it's phi2 minus phi1 over, because this is dEj, because we run this loop through the cell centers, but we do it for each individual edge. So for this edge, we use dEj. Let's see. Yeah, actually, we can call this. This should be in my notation. This is called L. Maybe it's okay. In this case, we'll just. Yeah, we'll use L. Just for length. I like that better. L. This is going to be L1, the length across the edge. And as you see, this makes perfect sense when you know about how the derivative is, like d phi dx, d phi dx is going to be, the gradient across this edge, and it's stored at the edges. We can make this pressure. Pressure here minus pressure here over the distance, that's the pressure gradient. So yeah, that's actually pretty nice. And if we want to make it more complicated, we could make this a flux function to maybe get a more higher dimensional derivative to basically get the values at this point. But I think this simple way of calculating the gradient is actually pretty good. Finally, we'll talk about curl. So it's E in EV of V, which is V is a corner. So this is basically the edges surrounding a vertex V. So maybe we have our vertex V, the edges surrounding it are 1, 2, or let's do this one. Our edges, vertex V, which is called Q1, is surrounded by this edge, and this edge. So we sum through those. So yeah, we actually have a diagram here. And we need this vector, at all of these edges, there's 3 of these t vectors. So we divide by the area of the dual mesh. So let's say we're talking about Q1, so V is equal to Q1. That's this right here. So Q1, this is Q1. We need the area of, when we say A, Q1, we need the area, or in fact, I think it might, yeah, it's an area of this dual mesh, the dual mesh which surrounds the vertex Q1. Then this one will be T of TEJ of Q1, so that would be, we're looping through all the edges. Let's do this edge first. Then we would use this T normal vector, which is to the right of the left of the actual the n normal vector. And we also need the length of this edge. We're going to call it LEJ, the length of this edge. Before when we talked about L, length, okay, that kind of interacts. Maybe we can use a different notation. So this D will mean the actual, okay, I see. I should change things. So this is L. L will be the length of the actual edge. Here, we're not, I believe, length, we're talking across the edge. This should be distance, DL, where D is this, distance from here to here. So that's why that's D, this should be D. Okay, and then for this one, we call it L because it's the length of the edge each time. Here we use D because it's the distance between the two centers. And then here, it's L again because it's the length. So, and the way we define T is, I guess it's contribution to the curl. So I think if it's, is it positive? If it's a positive contribution to the curl. So if the curl is positive, it goes this way. So there's some way it goes from away from Q1 towards Q1. Okay, I see. So if it goes towards Q1, we say it's positive, and if it goes away from, I see, for example, D1. Oh, they call it, okay, D1. Yeah, if it goes away from this vertex, it's negative. If it goes towards, it's positive. So this one is positive, this one is negative. So positive, negative, negative. And we just, run through with our fluxes. This will be, okay, I believe, I had this wrong. This is, sorry for the mistakes, this is D again. This is actually the distance between two cell centers. Or distance across an edge, which is between two cell centers. So we just, add up these contributions, in this case it will be, T1, let's do this part first, this edge, remember there's three edges, do this edge, it's this T times this distance times the flux, and T is negative here. Here it's going to be this T1, which is negative again, if you do the seventh one, and then the flux, and it's this distance here. So we're looking actually at the edges of this dual mesh triangle. Okay, and then the final one is going to be positive contribution for T, this D6 times F6. So you can see down here, it's this one, the first TI for edge 1, distance of the dual mesh across edge 1 times the flux at edge 1, and then same for the 7th, because this is 7, and then the same for this one, which is 6 right here. And we just need to take into account these numbers, and we actually now have a way to calculate the curl. So this is actually pretty powerful, because before I've actually never seen how you deal with the curl, and I kind of racked my head around it. I couldn't figure it out, and this kind of makes sense now. You can just do these, and I guess if you have some squares, it's something like this. I've never seen it been calculated before, so that's very interesting. Yeah, so later I do want to talk about this, but I don't have the knowledge currently of how to do this. But right now, for solving the momentum equation, we know how to treat a gradient. But as for the dot product of something with a gradient, or the Laplacian, which is, a gradient dotted with a gradient of something, how do we do that? I'm not exactly quite too sure. Evection operator, yeah, not sure. Laplacian, I do know for a scalar we have the answer, and it's this, which ends up looking like this. So it's the length of an edge times the distance across the edge times the difference of the scalar value at the edge minus the scalar value at the cell center. But as for a Laplacian of velocity, because scalars are stored at the cell edge, but velocity is stored at the scalars are stored at the cell center, so velocity is stored at the edge. So I'm not sure how this is done. The gradient of something stored at the edge is at the cell center, so I need to confirm how that is done before I can talk about it. And finally, we have the Coriolis force. This is I'm not sure how this works at all, because we can use the curl. I think there's some sort of curl. It's like F, or it's not a curl, but it's actually it's not a curl. It's something like F cross U. It's a cross product. I'm not sure how this is dealt with. So that's another future thing I want to know how to do, because this is very important, doing a full Coriolis force. There's a lot of terms that are also just based on the X and Y direction and stuff like that. So this is a future thing I want to think about. I also want to mention one last thing is, when we're calculating, the calculations of divergence, or for example, we are trying to solve something that I'm still left with confusion about is, when we talk about a Cartesian grid, we have, our ux, uy, uz, which we call u, v, and w. These are our velocities in the x direction, y direction, z direction. Well, if we're talking about a sphere, we can say u lambda, maybe, and then u phi and uz. These would be our longitudinal, latitudinal, and z velocities. How can we do this? Because, in our equations, normally we write it like this. It's du dx, dux dx, time, for example, dt, something like this. And we have a pressure gradient, something like this, dp dx, negative 1 over rho d partial p partial y. These are our equations, but how do we do that here? Because we know that u, v, and w are stored here. And, we know that p is stored here. Ux, uy. But, where is y? Where is x? We somehow need, a gradient. We only have gradients in these set directions, but it's unclear to me how we differentiate between different terms of our equation. I think the way it's sort of treated is like we have this general vector like this is equal to negative 1 over rho. And it's going to be partial p partial xi. How do we do this? I mean, I can sort of see what we just talked about. We can apply an actual 3D gradient, and we don't even have to split into our multiple equations. But how do we account for, we have three physical velocities, u lambda, u phi, and uz, or ux, uy, uz. And they have a specific direction to them, which is not perpendicular with the edges or the face. So, we could do that. But what do we get? We get a solution for u. I guess it would be, in this case, u would be a solution at the edges. But what is that u giving us? Does it include these multiple directions? How do we get it back to talking about those directions? So that's still of confusion to me. How do we do that? So in the future, I hope to figure that out, and then I'll share it with the channel if I do figure it out. So yeah, thank you. And next, I'll be taking a break from the numerical modeling series and just be talking about numerical weather prediction, just talking about some of the models that are used for that, and how they treat things, what kind of model settings they have, what kind of physics parameterizations, they're doing momentum equation, they're doing moisture, ocean, coupling, stuff like that. So I'll be moving on to that next. So stay tuned. Thanks.